We're ready for 5.5, which in my opinion is one of the more interesting sections that we do. Here's where we talk about complex eigenvalues, and today we'll find out how to find a complex eigenvalue, how to find the eigenvectors that go with it, how to interpret this kind of in a diagonalization way, in the same way that we thought of diagonalizing our regular eigenvalues and eigenvectors. And in the process, we'll have a little bit of thought about how to think about complex numbers in general, because that ties all into this. But let's just begin with this problem, and we'll just tackle it, and then as we go through this problem, you'll kind of see how we find and calculate complex eigenvalues. Okay, so the first thing we're going to do is we're going to do the same thing we've always done, and that is we do a minus lambda I, and we take that determinant and we set it equal to 0. So the determinant here is 2 minus lambda, negative 1, 5, and negative 2 minus lambda. And then we put this together, and what you'll see is that we've got 2 minus lambda times negative 2 minus lambda plus 5 equals 0. Okay, let's do a little bit of multiplying here. You'll actually notice this is a difference of 2 squares. So we get a negative 4 and then plus lambda squared plus 5 equals 0. This simplifies to lambda squared plus 1 equals 0. And now, if you remember, we could put it over here and get lambda equals plus or minus I. So our solutions here are imaginary. And in fact, they're the simplest imaginary solutions we could get. They're just plus or minus I. Okay, so this is how we find our eigenvalues, and you find your eigenvalues the same way you always have. The only difference is when you get to the end, you get imaginary numbers instead of real numbers. But now the question is, what do we do about eigenvectors? This is where it gets a little bit more interesting. And let's look at each one. And what we're going to do is we're going to cheat, basically. First, I'll tell you how not to cheat, and then I'll tell you how to cheat. But it's not really cheating. It's just cutting down on the effort. So we're going to start by finding our eigenvectors. So we'll do lambda equal to I. And we're going to try to solve 2 minus I, negative 1, 5, and negative 2 minus I, and 0, 0. Okay, so first thing I'm going to do is I'm going to do it in like the non-cheating way. And the non-cheating way is to ask yourself, how do I take a complex number and make it a non-complex number so that I can do some sort of row reduction with it? And the answer is you multiply by the conjugate. So what I'm going to do is I'm going to multiply both rows by the conjugate. And I can do either the conjugate of this or the conjugate of this. Let's do row 2. So I'll do row 2, and I'll multiply it by negative 2 plus I instead of negative 2 minus I. Okay, now let's look and see what happens when we get there. So when we do that, we're going to get, and let's just keep writing in blue the whole time. Okay, and let's see what we get. And so what we get is 2 minus I, negative 1, 0. And then here we've got 5 times negative 2 is negative 10. 5 times I is plus 5I. And then here we'll get negative 2 times negative 2 is 4. And then this is a conjugate, so we get minus 2I and plus 2I, so those cancel out. And then we've got minus I squared, so negative 4 minus I squared. But of course, I squared is negative 1, so that's the same as negative 4 plus 1, which itself is the same as 5. And now if you look, you'll see this and this are the same. So all we have to do is take 5 row 1 minus row 2. Actually, we're adding here, and put it into row 2. And that's going to give us 2 minus I, negative 1, 0, 0, 0, and 0. What I'm going to tell you is, so that works. You can always multiply by the conjugate and do the math if you want. But I'm going to give you the cheating way. And the cheating way comes from the fact that we know this is an eigenvalue. And since we know it is an eigenvalue, we know something has to happen. We know something must happen when we row reduce. And we know when we row reduce, we must end up with a free variable. So I'm going to do this problem again, and I'm going to do it the cheating way. I was going to write in red to make you kind of realize, but let's write in green, because green's like goes. This is good. So what I'm going to know is I'm going to know that we must get a free variable. Well, since we must get a free variable, that means whatever we do, we row reduce, and the second column is going to become all zeros. And so that means this thing is just going to be 2 minus I, negative 1, 0, and 0, 0, 0. So whenever you have a complex eigenvalue, you are free to skip the row reduction and just write a row of zeros. In fact, this happens every time we have a 2 by 2 eigenvalue. So you can always skip the row reduction and just write down the second row of zeros, because we know that's the way row reduction is going to go. This doesn't work for 3 by 3s or 4. It doesn't work for higher dimensions, but it does work for 2 by 2 because you have to get those zeros here. Well, okay. Let's try to interpret this in terms of a vector and see what does this mean. So our vector is gives us 2 minus I times x minus y equals 0, and it sure looks to me like it's easier to solve this for y than for x. So I'm going to write y is equal to 2 minus I x. And that means if I want to write this out as a solution, my vector solution xy is going to be written as a multiple of x, and x is equal to x, so it's 1, and y is equal to 2 minus I, so 2 minus ix. So what we notice is we got a complex number for our eigenvalue. We also get a complex number for our eigenvector. Okay, and it turns out that the two, if I did negative I, you would get the same thing with a plus sign here, and so it'd be basically, so you would have the exact same process except you'd have a plus I here at the bottom. Okay, so this was great. Well, good. Well, what can we do with this? What can we do representing this thing? So we can find the complex eigenvalues and complex eigenvectors. But what we want to do is I want to take and do something similar to this PD P inverse thing that we had going on. And let's think about that for just a minute. So we noticed that in the past, in the last time, we had a vector and we wrote it as P times D times P inverse, where this P was our two eigenvectors. Our D was made up of our eigenvalues, and then the P inverse was those two eigenvectors inverse. So we know that this is what we did in the past. Well, what we're going to do now is something that's almost the same, except we'll make just some very slight changes. Okay. The slight change is that now we usually use slightly different notation. I think usually the book uses a C maybe instead of the P in the middle. So let's write it as PCP inverse. What we're going to do is this C we're going to write as our eigenvalues, except notice every time we get complex eigenvalues, it will always be the same. It'll always be an A plus or minus BI. You're always going to get 2 when we're in the two-dimensional case. When you get to higher dimensionals, this all gets more complicated. But when you're in the two-dimensional case, we always get 2. One is A plus I at BI, and the other is A minus BI. You can see that this will come from doing your if you're in two-dimensional, this will come from doing the quadratic formula, and so you have that plus and minus term. So you always get the plus and minus, and the I shows up in the square root. This is just from the nature of complex eigenvalues as well. Complex numbers show up in these pairs. Well, what we're going to do is we're going to put the A, and then maybe the minus B here, and the A and the plus B here. You can switch which one you want. Oh, sorry, and then we do it the other direction. And then we do the A and the plus B. So you can kind of think of it as going A plus B, and then A minus B. But so we're always going to write our vectors, our matrix like this. We're always going to write it. So we're going to write our C matrix with our real parts here, and then our imaginary parts here, except we're going to put the negative on one of them. It doesn't matter which one you put the negative on. I'll always put it right there. Okay, so there's our negative one. Now, what you'll notice is that this C now looks like what we call a rotation, because if you remember, whenever we had our rotations earlier in the semester, we had cosine, sine, negative sine, and cosine. And so this kind of looks like those matrices that we know make rotations. And that's kind of the connection to the diagonalization. And in the last video that we make for the semester, I'm going to put a lot of effort in this because I have some neat visualizations for us to look at and so on. Okay, but if those are our eigenvalues, then our eigenvectors are always going to look something like this. We don't know what they are. They're going to have real and imaginary parts. So we'll have a real and imaginary part. So let's just do x plus yi z plus wi. And so for this, what we're going to do for this p vector, we're just going to take the real and imaginary parts and just write them as x, y, z, and w. So we're just going to write that out for our real and our imaginary parts. And then we'll have the exact same thing over here so we'll have that x and that y and that z and that w, and we'll have the inverse. So we take just any one of our eigenvectors and then we write it out in our matrix. Okay, so if I look at that problem that I did just a moment ago, what does that mean? That means for the problem that I just had, I get, for the problem I just had, my matrix, which was my matrix 2, -1, 5, and -2, is, so our eigenvector was 1, 2 plus I, so it's going to be 1 and 2, 0, and -1. And so what you can see here is you can see that our vector, let me erase all of this real quick. Okay. And then what you can see, because our vector was 1 and 2 minus I, so you can see how that vector got transformed into that matrix. And then our complex eigenvalues were plus or minus I, so you can think of them as 0 plus or minus I. So that means we'll have a 0 and a -1 and a 1 and a 0. And then finally we'll have the inverse of that. And notice the inverse means we switch those two, except I think we'll end up with the exact same thing, actually. I think that one is its own inverse. Let's think about why that is. So the reason is the determinant is -1. We switch those two places and we get negative and positive and negative, but then we divide by -1 and it makes it positive, positive, and negative. So we end up with the exact same thing we started with. So that function happens to have the same inverse. Don't count on that normally happening. Usually there's going to be something else going on. And this is the inverse. So this is our matrix. Maybe I should check that it actually works. I'm a little bit worried about checking, but let's go ahead and do it. So let's look at these two on the right first, and we'll get row times column is -2, row times column is +1, row times column is 1, row times column is 0, and so we'll get that multiplied by 1, 0, 2, -1, and we'll get row times column is, I am off by a negative sign, aren't I? I wonder if I should have put the negative here. Let's keep going and see if it's all off by a negative sign. Row times column is -2. Row times column is 1. Row times column is -2 minus 1 is -5. Row times column is a +2. Yeah, notice I'm off by negatives, so my guess is I should have put negative here and positive here. And if I were more careful, I would actually go read and make sure that I'm being careful that I'm getting my right positive and negatives. My guess is that we put the -1 here because this first column vector, because the vector we used was 2 minus I, so we're going to put the positive I in that upper right hand corner. So we're going to do like positive. So if you remember, we did lambda equal to I, and then our vector was 1 and 2 minus I. And so I think since it was positive, we probably use that positive in that corner. I'm a little uncertain about this, but my guess, and I guess we could check it. Let's go ahead and do it because, hey, I've got time. My guess is that if I'd used the other eigenvalue, which was -I, then our vector would have been 1 and 2 plus I. So let's see how that would have changed the game if we'd have done that. So that would have been 0, and that would have been a +1. This one now would have been a -2 would have been here to make that work out. And my guess is that if I made that a -2 and made that a -1, then maybe that works out to give me the correct answer here. So if this works, then what I'm believing is that whichever eigenvalues you should write it on that first column, and then the other one on the second column, kind of the complement or the conjugate of it in that second column. So here's our eigenvalue. Let's see, is this the inverse? We switch those two, put negatives on that. The determinant is 1. Okay. Okay, so this becomes 1, 0, 2, 1, and let's multiply here. Row times column gives me a positive 2. Row times column gives me a negative 1. Row times column gives me a 1 and a 0. And let's check. That times that gives me 2. That times that gives me negative 1. 4 times 1 is 5. And negative 2. Okay, so that works. So I believe that we have to be careful, and whichever eigenvalue we chose to make our eigenvector out of, that eigenvalue needs to be the top column, and that's the one that, or the top row, and that's how we need to set them up so that they work correctly. Okay, so be a little bit careful as you put those together, but you can always check. And what probably, if you're off, that probably just means that you switched them somehow. Okay, so let's go back to what we had originally, which where I had a negative 2 here, and I should have had a negative 1 here and a negative 2 here. So I think that's what I originally had. And let's take a quick observation and notice what's going on with this vector. What is this matrix? Well, this matrix happens to be a 90-degree rotation, because this is the matrix that takes these two, E1 and E2, and transforms them so that E1 goes to 0, negative 1, so this is my new E1, and E2 goes to 1, 0, and so it goes to that one. So it is a 90-degree rotation. So my box now got moved to be that box. So my box got rotated 90 degrees, in this case clockwise. So if I'd used the other one, it would have been a 90-degree rotation the other direction. But what's nice is that means that whereas in the past, whenever I had my middle vector made up of my regular eigenvalues, what those values did is they stretched these things. Well, now a complex eigenvalue means you have a rotation. And what you'll notice is that if you have a rotation, it makes sense you wouldn't have any eigenvalues, because if the whole space rotates, then that means every single vector has rotated, so no vector is pointing in the same direction that it was originally. So in this sense, it's kind of logically consistent that rotations should result in complex eigenvalues and not real eigenvalues. Okay, so when we have complex, we get a rotation here in the middle. We're going to talk a lot more about this as we go on, but the big summary, but that's one of the big summaries. Okay, what I want to do is I want to cut the next couple sections. So section or exercise 5.24 is a little bit kind of getting into the weeds. Not in the weeds. I really like it, but exercise 5.24 and 5.25 is just kind of saying some of these things I was talking about in a rotation in more detail. So let's cut over those and cut straight to 5.26. And what I want you all to do, and we'll do the same thing we've always done, start with 5.26, see if you can find those complex eigenvalues and eigenvectors, and see if you can write a vector that's a rotation in the middle with your eigenvectors on the outside. So good luck on 5.26. And when you finish that, we'll do the same thing with 5.28, and that will be our exercise for this section.